To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.
Hello my dear students, welcome to today's lesson. Today I am going to discuss with you all exercise 13.2 in your textbook. So like I said in the previous chapters, we have discussed what will happen when current flows through a conductor. You all know there will be magnetic field generated. That is how the electromagnets work. And then you were able to understand when we place a conductor in a magnetic field and allow the current to flow through it, there is a force generated. And this particular force, the direction of the force depends on the direction of the current flow and the direction of the magnetic field. And because of that, we use the Fleming's left-hand rule to identify the direction of the force. But before that, when we saw the magnetic field induced magnetic field when current flows through a conductor, to determine the direction of the magnetic field, we use the right-hand grip rule. So if this is the conductor, we use the right-hand grip rule or the corkscrew rule. So you're familiar with all these concepts. Then after that, in the previous chapters, I discussed the loudspeaker, the function of the loudspeaker, and also the parts of a direct current motor and the function of a direct current motor. So these questions are related to that particular concept. Exercise 13.2. The first question, the figure below shows how a student used his left hand in order to apply Fleming's left-hand rule. So here you can see all three fingers, the thumb, index finger and the middle finger, they are perpendicular to each other. They have been labeled as A, B and C. And the questions are given to you. For what purpose is Fleming's left-hand rule used? For what purpose? To find the direction of the force when a current is flowing through a conductor placed in a magnetic field. So that is why we use the Fleming's left-hand rule. That is what you need to write there. To determine the direction of force acting on a conductor placed in a magnetic field when current flows through it. So just by placing a current carrying conductor is not enough, but current has to flow. There should be magnetic field and then there will be a force, and that will be determined using the Fleming's left-hand rule. Then directions of what physical quantities are represented by the fingers A, B and C in the above figure. So when you hold your left hand like this, thumb, index finger and the middle finger perpendicular to each other, you all know the middle finger, that is the current flow, direction of the current flow. And the index finger is the direction of the magnetic field and the thumb shows the direction of the force. So here this will be the force. This is the magnetic field, or I'll just write it as field there. Field, and this is current. So those are the three fingers. So if you are to write for fingers A, B and C, A is the magnetic field. Here the letters are given in a different way. A is magnetic field. Then B, here you can see electric current. So the finger A is the magnetic field, that is the index finger. Then middle finger B is the electric current. And C, that is the thumb, is the force. So those are the quantities, directions of what physical quantities. So here we don't have to say direction of magnetic field, direction of electric current and direction of force, because already they have mentioned it in the question. But if you write it that way also, it's fine. It's just that they want you to know the physical quantities represented by each finger. So if you hold your left hand, this is the force, this is the magnetic field, and that is the current flow. So if it is this way, the force is acting upwards. Why? Magnetic field is from north to south in this direction, and the current is flowing towards you all. So then the force is upwards. Is that clear, students? So that is how we use the Fleming's left-hand rule. With that, I will move on to the next slide. Third part of that question. Write down what happens to the wire in the following cases using Fleming's left-hand rule. So here they have shown the wire. Now the first one. Here you have to look at the magnetic field and the direction of the current flow. I have explained this with the motor, working of the direct current motor. With that, I explained to you all, when we change the direction of the magnetic field, what happens? When we change the direction of the current flow, what happens? All that we have discussed. So now here you can see the magnetic field, north pole is here, south pole is here. So the magnetic field has to be this way. Then current is flowing in this direction. Now we will consider only this part. So here current is coming out. Current comes out, goes in there. So the magnetic field is this way, current is flowing outwards here. So magnetic field this way. Then what is the direction of the force? Downwards. Here the direction of the force is, this side is going to move downwards. The same way if you take this, you can see current is flowing into the board. So it's here, magnetic field this way, north to south. So the force is upwards. So here of course force upwards. Then how will the coil rotate? It will rotate in this direction. What is that direction? It is the anti-clockwise direction. Anti-clockwise. Then if we take this one, I will use a different color so that it's easy for you all to understand. Now here, north to south. You can see north here, south there. The current flow is the same, like this, plus and minus. So now the field is going to be this way. If you consider this one, current flow is going to be the same. So current will come this way, the field is that way. So the force is going to be upwards on this side. The same way here if you apply, north to south, current goes in. So the force is downwards. Here, force is downwards. So how will the coil rotate? It will rotate this way. Clockwise rotation. Is that clear? So can you all compare the difference? Only thing is the magnetic field. Here it is south to north, here it is north to south. So when it is south to north, it's anti-clockwise. Here it becomes clockwise. That is, the current flow has not been changed. Then, so here again we have another instance where you have south to north the same way. Can you see that? The magnetic field is the same, but the direction of the current flow has changed. The current flow is going to be this way to this way. Then, how will it move? So, magnetic field has to be in this direction. Now, here current is flowing into the board. So, the force is upwards. So here the force is upwards. Now here current flows this way, current is flowing out, field is this way, so the thumb points downwards. That means the force is going to be downwards. Then how will this rotate? It will rotate in the clockwise direction. Clockwise direction. Is that clear? So when you compare these two, here the poles of the magnet are changed, here the direction of the current flow has been changed. Only one change has been done. Now look at this one. When you compare with this, you can see north-south. The magnetic poles are the same north-south, but here the current flows in from here. Here the plus and minus, so current flows this way. Again, if we use a different color. So here, of course, the current flow is going to be like that. So then, if you take this one, current is going in, field is this way, the direction of the force downwards here. And if you take this, north to south, field is this way, current is flowing out, the direction of the force is upward. So this is going to be an anti-clockwise rotation. Compare these two. Why? Current flows in from here and comes out this way, clockwise. Current flows in from here and comes out that way, anti-clockwise. But if you remember, I told you all, when you change both, when I did the lesson, I told you all this. When we change both the direction of the magnetic field and the direction of the current flow at the same time, compare this and this. South to north, north to south. Current flows from this way and comes out this way. Here current flows this way and comes out there. So both have been changed. Magnetic field is changed. Direction of the current flow has been changed. But the direction of rotation, can you see, remains the same. Is that clear now? I told you all to try that on your own. I'm sure you would have done that. So when you change the direction of one factor, the direction of rotation changes. But when you change both factors simultaneously, both quantities simultaneously, then of course the direction of rotation remains the same. If you compare these two, here also you can see magnetic field north to south, here magnetic field south to north. Here the current flow is through this plus to minus, here it is in the opposite direction. Again you can see both of them, the rotation is clockwise. So when both factors are changed, the direction remains the same. But when you change only one quantity, then the direction of rotation changes. So like that you have to get the idea. That's the important thing. You have to always apply the Fleming's left-hand rule and you have to get the concept. Is that clear, student? So with that, I will move on to the next slide. So this is the second question. The figure below shows the cross-section of a loudspeaker. So here you can see the cross-section, students. You all have studied that in the lesson. Now the parts have been labeled as A, B, C and X. So you all know. Now this black color line outside is the outer metal case and that is connected to the B part, that is the cardboard cone, and here you can see the wider diameter is attached to the metal cone, and here you can see this part is again around the magnet as well. So what is labeled as A is the ring magnet. You can see north, south, north, the poles of the magnet, and what is labeled as C, you can see inside, that is the coil, the wire coil, and then X is what? The input. What is the input here? It is the varying current. varying electric current. That is what we supply here. The current flows through this as well as the coil. And since there is the magnetic field and the current flowing through the conductor, there is a force generated that makes the cone to vibrate or to move back and forth. You all know the cone is connected with the metal frame in such a way that here you can see the red color lines move freely actually. So that is the cross section of a loudspeaker. Then here, first question, labels parts A, B and C of the figure. So there, A, B and C. What is A? A is the ring magnet. Then what is B? Cardboard cone. Cardboard cone. And C is the coil. So A is the ring magnet, B is the cardboard cone and C is the coil. Then second one, write down a special characteristic of the current entering from the terminal X. From the terminal X, like I told you all, it is the varying electric current. So that is the special characteristic. It is the varying electric current. And why is it varying? Now, like I told you all, normally we talk on the microphone or either sound waves are given to it. So then what happens? According to that sound wave, it can be music, it can be a speech. Either way, the sound wave, the pattern of the sound wave will vary. Based on that, in the microphone, there is an electric current generated. And that will be a varying electric current. So that will be given to the part that is labeled as X. Then, explain the operation of the loudspeaker. So, how do you explain the operation of the loudspeaker? Here you can see the varying current enters through this. So, here there is the conductor and there is a coil around it. And when the current flows through the coil that is placed within the magnetic field, across the magnetic field. Here you can see the magnetic field. What happens? There is the force generated. And according to the Fleming's left-hand rule, you can actually find out the force. You will see that the coil will move back and forth like that, depending on the current. Now, if you don't give a varying current, again there will be no movement. If it is a continuous current, then the force will be only in one direction. Only when it is a varying current, there will be a movement. So, that is another reason why the current has to be varying current. So, what happens there? Due to that, due to the movement of the coil back and forth, there will be a vibration. And here you can see with these red color components, the cardboard cone is connected to the coil. So, with the coil, the cardboard cone also starts to vibrate. And that generates sound waves. How does that happen? There are air particles here. When the surface is vibrating, that is the cardboard cone is vibrating, there are air particles around it. In front of it will also start vibrating. So, vibration of air particles will carry the sound energy. So, therefore, they become the longitudinal sound waves. I'm sure you all can remember that. So, that is what you need to write here. So, here we can say when a time varying current flows through the coil placed in the magnetic field, there is force generated. Due to this force, the coil moves backward and forward. The smaller diameter of the cone is connected to the coil in such a way that it vibrates along with the coil. This movement, or you can say vibration, of the cone generates the sound wave. Is that okay, students? So that is the explanation there. When a time varying current flows through the coil placed in the magnet, it should have been magnetic. It should be magnetic field. Magnetic field, there is force generated, and due to this force, the coil moves backward and forward. The smaller diameter of the cone is connected to the coil in such a way that it vibrates along with the coil. And there you can see this movement or vibration of the cone generates the sound wave. So that is how the loudspeaker functions. I'm sure you all also have written a similar answer. So with that, students, I'll move on to the next question. So here, fourth part of the question, write down the energy transformation taking place in a loudspeaker. So like I told you all can remember, we supply the electric current, so it is electric energy. Then when there is the force acting and the vibration occurring, it is the kinetic energy, or what we call as the mechanical energy, because kinetic energy is a type of mechanical energy. And finally, it is the sound energy that is generated. So electric energy becomes mechanical energy, and then finally the sound energy. Electric energy becomes mechanical energy, that in turn becomes sound energy. So earlier also I told you all these students, we supply electricity, we get the sound. So you can also write it as electric energy to sound energy, skipping this middle part. But you all have to understand that when there is the back and forth movement, then there is kinetic energy. That means there is mechanical energy. Is that clear, student? So then we look at the last part. Write down the functions of each of the parts A, B and C. So A, what is A? Is the ring magnet. What does that do? It provides the magnetic field. A, ring magnet, provides the magnetic field. Then B. What is B? B is the cardboard cone. So cardboard cone, what does that do? Cardboard cone moves back and forth, or you can say vibrates and generates the sound wave. Because of that movement only sound waves are generated. Then C, you can see in the diagram, it is the coil. Coil is the conductor placed in the magnetic field. So coil is the conductor placed in the magnetic field, and the force acts on it. The force acts on it when a varying current flows. So that is the purpose of having the coil. So you're familiar with all the components. A is the ring magnet, provides a magnetic field, and B, cardboard cone, moves back and forth, or you can say vibrates and generates the sound wave. Then C is the coil, is the conductor placed in the magnetic field, and the force acts on it when a varying current flows through it. So those are the functions of the different parts. With that, students, I'll move on to the next slide. So here we have the next question. The figure below shows the main parts of a DC motor. So when we say DC motor, you all know it is a direct current motor. So here, as you look at the diagram, I'm sure you all can identify the parts. So if we look at it, here you can see what is labeled as K is a switch. Then E is the potential difference, or the battery dry cell is shown there. Then you can see P and Q. You all know those are the brushes of the commutator. Then what is labeled as X and Y are the split rings of the commutator. So all these together, the two brushes and the split rings together are known as the commutator. Then here you can see the terminals are connected to this loop, wire loop, that actually represents the armature, the wire coil. So here it is a wire loop A, B, C, D. And here you can see north to south, that is the north pole and the south pole, which is also labeled as V and U. That is the magnetic field. North to south is the magnetic field, and they are the magnetic pole. So you can identify all the components there. Then, first question, label parts P, Q of the above figure. What are P and Q? P and Q are the brushes. Brushes. So that you know, part of the commutator, they are the brushes. Then we'll move on to the next part. Second question, what are the components labeled X and Y? So like I told you all, X and Y are the split rings. Split ring. Then third one, indicate the direction of current flow in terms of the letters given when the switch K is closed. So you can see when switch K is closed, if we mark it in the diagram, that is the positive terminal. So current will flow this way to P, then to X, then here to A, from there B, C, D, then to Y, Q, and back to E. Is that clear? So we need to use these letters mainly. P, X, A, B, C, D, Y, and Q. So there P, X, A, B, C, D, then Y and Q. I am writing A, B, C, D together because that is the loop, part of the loop. But these are different components. P and Q are the brushes, X and Y are the split rings. Is that clear? So the direction of the current flow is that P, X, A, B, C, D, Y and Q. With that, we'll move on to the next question. So here, what is the direction of rotation of the motor when switch K is closed? So when switch K is closed, what will happen? We have already seen current flows this way and comes out this way. So here, what is the rule you need to apply? The Fleming's left hand rule. So north to south, the index finger is the field, middle finger is the current, and thumb points to the direction of the motion. So here the field is this way. If you take C and D, current is flowing outwards towards you all. So the force is upwards. Force upwards. The same way if you take conductor, the loop AB, magnetic field is still that way, but the current is flowing inwards, A to B. So the thumb points downwards. So that means the force is acting downwards. So this will go up, CD will move up, AB will move down. Then what is the direction of the rotation? It's going to be like that. So that is clockwise rotation. Clockwise rotation. Is that clear, students? So you have to apply the Fleming's left hand rule, and I'm sure once you get used to it, you don't have to apply for both sides. Once you apply for one part of the loop, then you know obviously it has to rotate continuously. So let's say if you apply for AB, you know the force is acting downwards, then from there itself you can understand it's going to be a clockwise direction. But just to make sure, you can, or it's better if you apply for both parts. But like I said, once you get used to it, you can just determine the direction using the direction of force either on AB or just CD alone. Is that clear, student? So then, fifth part of the question, write down the functions of each of the components given below in the motor above. So the motor is given to you. I have explained the parts. You can see V and U. V and U are the magnetic poles. So you know the function. What is it? Provides the magnetic field. I'll rewrite that. So here it provides the magnetic field. Magnetic field. Field. Then we have B part is E. What is labeled as E? You can see here it is the battery. Provides the current. Provides current. Because it is the dry cell. Then P and Q. What are P and Q? Brushes. P and Q, brushes. What are the function? What is the function of the brushes? Provides contact with the split ring so that current flows. So here brushes provide contact between the split rings and the terminals of the connecting wire. so that current can flow. Then X and Y. What are X and Y? The split rings. X and Y split rings. Rings help to alternate the direction of current flow through the wire loop. So, the split rings help to alternate the direction of current flow through the wire loop. Those are the functions. So, here you can see V and U, they are the magnets. So, they provide the magnetic field, and E is the battery, so provides current. And P and Q, they are the brushes. Brushes provide contact between the split rings and the terminals of the connecting wire. And X and Y, they are the split rings that help to alternate the direction of current flow through the wire loop. So, together it is the commutator. Even the function of the commutator is also the same. Commutator helps to alternate the direction of current flow through the wire coil. I am sure you all can understand that. So, with that, students, I'll move on to the next slide. This is the last part of the question, part 6. Write down the changes that take place in the operation of the motor under each of the changes given below. So, here the diagram that is given to you is the same as before. Now, you can see north and south. And also the current flows in this direction. You can remember. So, if we apply the Fleming's left-hand rule for part of the loop AB, you know the field is in this direction, current is going that way. So, the force acts downwards. So, the rotation is going to be what? Clockwise rotation. So, that is what is shown there. But if you interchange the battery terminals, interchanging the battery terminals, so then what will happen? If you interchange the battery terminals, now here then of course the terminals, if this is changed, then what will happen? Current will flow this way. Current will be flowing this way. That is C to D direction. C, D, B, A direction. Then what will happen? If it is C, D, B, A, current will flow from B to A, that is towards y'all. But still the magnetic field is that way. So, BA will move upwards. If BA move upwards, you know the rotation is going to be anti-clockwise. So, there it will be anti-clockwise. Like I said, students, I am not applying the rule for both sides, and also you are familiar with this concept. We discussed it in the lesson, and also in one of the previous questions, we saw what will happen if we change the direction of the current flow. So, I told you all, if you change just one factor, the direction of rotation will change. Then, here the next one, increasing the strength of the magnet. What happens there? You can remember the force depends on 3 factors. What are they? Length of the coil, the strength of the magnet, and the amount of magnitude of current flow. So, here strength of the magnet, and all the factors are directly proportional to the magnitude of force. So, when you increase the strength of the magnet, the magnitude of force will increase. So, the coil will rotate faster. So, there you can say speed of rotation will be fast. Speed of rotation will be fast. Why? Because the force is greater. Write down the changes that take place in the operation of the motor under each of the changes given below. So what do you think if you increase the current flow? Then also the speed of rotation will be faster. Why? The force will be greater. So you all know force is equal to mass into acceleration. The mass of the armature won't change. The load will not change. So then acceleration has to change. So that means it will rotate fast. Is that clear, students? So now you can figure out how we change the speed of a fan. You can make it to rotate slowly. You can make it to rotate fast. So that is how we do that. So those are the questions given in your textbook, students. So I'm sure you all also answered these questions correctly, and then you have confirmed it with my discussion. So with that, students, I'm going to end this chapter, and in the next chapter we will be discussing another topic, that is electromagnetic induction.
To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.